Assalamu alaikum. This is 191017 Yasir Zahid. This is part 1 of our lab number 9. In part 1 of lab number 9, we are simply supposed to add two 8-bit numbers. Now here we have stated our module, named it as lab 9. We have our two inputs A and B and our sum. Here we have stated our first input to be of 8-bit and second input to be of 8-bit, our output to be of 8-bit, and then we have our sum, which is A plus B. And here I have already compiled the code. You can see here we have got 0 errors, and then you can see here we are simply in RTL view we are adding these two numbers and we are getting their sum in the form of 8 bits. Now coming to its waveform file, here you can see I have taken two numbers. Our first number is 10101010 and our second number is 01010101. Now we will simply compile the code to add these two numbers. And now here you can see we have got our both numbers added and it shows 1111, which is the addition of these two numbers. So this is all for the first part of our lab number 9. Now we will move to the second part. Assalamu alaikum. This is 1917 Yasir Zahid. This is part 2 of lab number 9. In part 2 we are supposed to have carry input with addition to the two 8-bit inputs we already had, A and B. So here we have inserted an additional port, that's Cin, and we have declared it to be an 1-bit input because it can either be 1 or 0. And for sum we have made sum equal to A plus B plus Cin. So it's a sum of three things including carry in. I have already compiled the whole code and you can see here we have got 0 errors. Now I will be moving to its RTL view. Here you can see we have our two 8-bit numbers A and B, and our carry in goes here to the sum and is added the sum of these two A and B, and we get our 8-bit output. Now since we don't have a carry out, so we will have to keep our number small. Now coming to its VWF implementation, you can see here we have got A, we have got B. I have set A to 10101010 and I have set B to 010101 and 00. The last two bits have been set to 00 because we don't have the capacity for C out. So I have set it to 00, which makes the space for only the last 0 here, and which will be our carry in, which will indicate whether our carry in worked or not. So here we can set our carry in either to high or low. Here you can see 1 or 0. These are the only two values we can get, and we'll see what our sum becomes. Now I have already compiled it for both the cases, our high and low. First of all, going for low, we have got our output as 111111 and last bit is 0 since we don't have any carry, and our carry here you can see is 0. Now coming to when our carry is high, you can see right here we get 11111 and even our last bit is 1 because we have our carry in as high. So this is all for this part of the lab, the addition of two 8-bit numbers with carry in. We will move to the third part of lab. Assalamu alaikum. This is 191017 Yasir Zahid. This is part 3 of our lab number 9. And what we have got here in part 3, in addition to what we already had, is carry output. Now what we'll do here is we'll sum our two 8-bit numbers, and in case we have got our carry out, we'll get to know that. Now for that purpose we have declared our two 8-bit inputs as A and B, our first 8-bit output as sum, and our second output as carry out. We have declared a wire of 9-bit, that's temp, and in it will store the sum of two numbers A and B. Now our first 8 bits will be the sum of these two numbers, and our 9th bit as stored in wire will be our carry output. And this is all for the code part explanation. Now we will move to its RTL view. You can see right here we are adding two 8-bit numbers, and after their addition we get our output as sum, and our 9th bit, our last 8 bits as sum, and our highest, the most significant bit as carry output. Now moving to its waveform view, You can see here I have set first number to 1111 and second number to 0000. I can either set it to one the highest to get our carry output, and to the lowest to not get our output. That and so I have already run and compile this code for both the conditions. First of all, coming to our 1111 and 000, so we'll get our 1111 our A as it is on output here, and we won't get any carry out. So you can see here we have our carry out as 0. Now for the second condition, when we add these two numbers 1111, 8 ones and 8 ones for A and B, we will get 8 ones followed by a 0. So the last 7 ones and 0 will be here in our sum, you can see right here, and our carry output will also be high because we have a carry. So it's ultimately the 9-bit number of 8 ones. Last 8 bits are our sum and our first bit is. So that's all for this part of the lab. Now we will move to the part number 4 of lab. Assalamu alaikum, this is 1917 Yasir Zahid and this is part 4 of our lab number 9. Now in this part what we are supposed to do is we are supposed to have our carry out and carry it in addition to A, B and sum we already had. So we have declared our inputs, our 1-bit input as being carry in, our 8-bit inputs as being A and B, our 8-bit output as being sum, and our output being carry out. And also we have declared our temporary wire as 9-bit because the first 8 bits are going to go into the sum and the 9th bit is supposed to go as carry out. Now you can see here I have already compiled the code and I have got 0 errors and 0. You can see right here we are adding both the numbers along with the carry in, and then what we get here as output is our carry out and our sum. Our carry out and our sum. If we close this window, yes, our carry out and our sum. Now coming to its waveform, you can see here I have got two numbers A and B, first number being 11111000 and the last number being 0000111. Now adding these two numbers will result in 8 ones, and in addition to them when we add our carry in, which is 1, we can set it to 0 or 1, but in case I set it to 1, we'll get our output as 1 followed by 8 zeros, which means our carry out will be 1 and our sum will be. Modifying our result, I've already run this simulation. You can see right here this I have got as carry in A, B, which I provided. Our carry out is 1 and our last 8 bits are 0, which means 1 followed by 8 zeros, which is the sum of these numbers. So we can conclude that we are getting our carry out accurately. And this is all for this part of the lab, and now we will move to the 5th part of lab. Assalamu alaikum, this is 1917 Yasir Zahid and this is part number 5 of our lab number 9. So what we are supposed to do in lab number 9 is we are supposed to perform the function on these two inputs, which are A and B, which are our 8-bit inputs, and we are supposed to decide that whether we should perform addition or subtraction. Now to decide that, we'll use selector, which is our 1-bit input. Now to make this happen, we have declared all of our outputs as registers, and we are monitoring all our inputs using always condition, and then we have enclosed both of our conditions in begin and end. And now for condition, when selector equal to 0, we have brought the code for addition, and when it's equal to 1, we have brought the necessary code for subtraction. And this is all for the code part. Now coming to its RTL view, if I can generate its RTL view, I think I closed it, how I performed it earlier. So this is the RTL view. You can see here for addition we are adding both the numbers, while for subtraction we are adding first number and its complements of 1. You can see here it's not, and it's ultimately going to give us subtraction, as we know from our Boolean algebra course. Now coming to the waveform file, you can see here I have taken two numbers, 5 ones and 3 zeros, and the second number as 5 zeros and 3 ones. Now when we add these two numbers, what we get is 8 ones, 1 1 1 1 1 1 1 1. And then when we add another one, which is our C in, we are going to get 1 followed by 8 zeros. So here we can change our selector to be low or high. So now coming to its part where I have performed the simulation. So first of all, going for the addition, you can see here we have got our selector as 0, which means this is addition, and 1 1 1 plus this equals 8 ones, and 8 ones plus our C in, our carry in, which is also 1, will result in 1 followed by 8 zeros. So last 8 bits being 0 are provided here at the output, and our first bit being high is provided at our carry out. Now coming to the part where we are performing the subtraction, you can see right here the carry out and carry in are not necessary, as we have used only A and B for the subtraction. Now subtracting from this first number the second number, what we are basically doing is we are subtracting from 1 0 0 0 the 1 1 1 1. In short, we are subtracting from 8 7, so we get 0 0 0 1, and the initial 4 ones remain as such. So this is the subtraction part. This is all for the part 5 of the lab. Now we will move to the part 6 of the lab. Assalamualaikum, this is 191017 Yasir Zahid, and this is the last part of our lab number 9. So what we are supposed to do in this part of the lab is we are supposed to take two inputs of 4-bit, namely A and B, and on the basis of our 4-bit input, namely selector, we are supposed to decide that what are we going to get on this output. So we were supposed to select on the basis of our own choice that what 10 functions should we perform. I have chosen these 10 functions, and I have written these down in front of each in the form of comment, being sum, difference, modulo, logical AND, logical OR, less than, greater than, bitwise AND, bitwise OR, and bitwise XOR. Now the method I have used here to perform this is using the case statement. First of all, I have declared all the inputs. I have taken always of all the inputs to monitor them, and then for the case I have selected my 4-bit input, which is selector, and then for each case being 0 0 2 1 0 0 1, I have given it the function it's supposed to perform in front of it, and default case is wrong value, and here we have ended our whole program. Now you can see right here I have already compiled the program and it has got 0 errors. Now moving to its RTL view, you can see right here it's a quite lengthy diagram, but these are all my 10 functions that I will be performing, and the output I will be getting here, and my program is supposed to decide that what out of these am I going to perform. Now moving to its waveform, here you can see I have got one selector line, one input A and one input B. Now what we are going to get is, on the basis of the value we select for our selector from 0 0 0 0 to 1 0 0 1, we will be performing the function that we have assigned and getting it at our output. So I have already performed all the 10 functions. Here you can see from 0 0 0 0 0 1 2 3 4 5 6 7 8 9 and up to 10. So now I will be explaining them one by one. Coming to the first function, which was for the sum. So first of all, we have taken the sum of these two numbers, this being A, selector is 0, which means we are taking sum, A being 1 0 1 1 and B being 0 0 1 0. Its sum is ultimately 1 1 0 1, which is 1 2 and 8, which means 11. 11 plus 2, we have got 13, and here you can see 8 plus 4 plus 1 becomes 13. Now coming to the second part, for 2 we had selected our program to do the difference. Now for the difference, you can see here, this here 0 0 1 means we are taking the difference of these two numbers, A minus B equals 1 0 0 1. Our 1 plus 2 plus 4, 1 plus 2 plus 8, sorry, 11 minus 2, which ultimately equals 9. 8 plus 1, 9. Now coming to the next part, which is our third part, it's the modulo. Now taking the modulo of this 13 with respect to 2, we'll get 1, because for 12 it's evenly divided, and for 1, this part here means we are first number, which is 13, with respect to b, which is 2. So 13 modulo with respect to 2 equals 1. Now moving to the next part, which is our this was the part we have selected for logical AND. So logical AND, this here 0011 means we are going for logical AND. Now for logical AND gives 1 only if we have an input. You can see this also has some value, A has got some value, B has got some value, so we'll get 1 at our output. Now the next part is logical OR. Logical OR means the part, if any of these values is high, it's supposed to give us 1. We can see here first of all this 0100 means we are taking it for logical OR. Now this you can see here has got some value, this also has got some value, so we'll ultimately get 1, which means both the values were having some value of high. Now next part is the less than. Moving to the less than part, we'll compare these two numbers A and B. Now whether A is less than B, so no, it's not less than B. This selector part 0101 means we are comparing it for less than. Is 13 less than 2? No, it's not, so we got 0 at our output. Now moving to the next part, which is greater than. This part, this selector 0110 means we are comparing it for greater than, and you can see here we are comparing these two numbers. So first number is 13, second number is 2. Is 13 greater than 2? Yes, it is, so we have got at our output 001, which means a high value, which is indicating yes, the first number is greater than the second number. Now moving to the next part, being our 8th command, which is bitwise AND. Now bitwise AND is supposed to give us, first of all, this selector being 0111 means we are performing bitwise AND. Now we have got our first input as 13 and second input as 2. Now so coming to our third least significant bit, we can see here for our first one and this 0, these both are not 1, so we'll get 0. And for these two cases also, these respective bits are not 0, and only its third bit for the both, which is 1. So we are ultimately going to 1 here. So this is the bitwise comparison of both these numbers, known as bitwise AND. Now moving to the next part, the second last part, the 9th command. This selector being 1000 means that we are performing bitwise OR. Now what we'll get here is we have got our first input as 13, second input as 2. Now comparing these, one of these is 1, yes, we'll get a 1 at our least significant bit. One of these is also 1, yes, we'll still get the 1 at our output. So both these are 0, so we are supposed to get 0 as our second most significant bit, and in this we have got 1 in the most significant bit, so we'll get 1, resultantly getting 1011. Now coming to the last part, our 10th command, which is bitwise XOR. XOR is also known to be the odd ones detector. It gives 1 only when one of the both ones is 0, when one of the both bits of the numbers is 0. Now first of all, this selector part being 1001 shows that we are performing XOR, bitwise XOR. Now this is our first part and this is our second part. So first bit, so here you can see we have got 1 1 and 1 0. So XOR gives output as 1 only if we have odd number of 1s. We have odd number of 1, so we got 1. Now moving to the next part, where we have got both as 0, we have got none of them as 1, so we will get 0. Now in the third bit here, we have got both as 1, which means the even number of 1, so we will get 0 because we get 1 only when it's odd. Now coming to the last part, we have got 1 1 and 1 0, which means we have got odd number of 1s, so we will get 1 at output. So these are the 10 commands we made our program for, and this is all for this part of the lab. This was the last part of the lab, and I hope it sums up the lab. Thank you and Allah Hafiz.